The grow and shrink algorithms for vectors both need to test whether a vector is superfluous. So we need a criterion for testing that. So here it is. For any set of vectors and any vector v in that set, if v can be written as a linear combination of the other vectors in that set, then it's not needed. Span of the set without that vector equals span of the set with that vector. And here's the proof. Let S be the set of vectors v1 through vn. And suppose vn can be written as a linear combination of the other vectors. We need to show that every vector in the span of S is also in span of the set obtained from S by removing vn. Well, every vector in span of S can be written as a linear combination of the vectors v1 through vn. Substituting for vn in this expression, we obtain v equals this linear combination, where notice that vn does not appear. We can rewrite that so that it's obvious it's just a linear combination in the vectors v1 through vn minus 1. And these are the coefficients. So this shows that the vector v, arbitrary vector in span of S, can be written as a linear combination of the vectors in S minus vn, and is therefore in the span of that set. That completes the proof. We say that vectors v1 through vn are linearly dependent if the zero vector can be written as a non-trivial linear combination of those vectors. Non-trivial means that at least one of those coefficients is non-zero. In that case, we'd refer to this linear combination as a linear dependency in the vectors v1 through vn. On the other hand, if the only linear combination that yields 0 is the one where the coefficients are all 0, we say the vectors v1 through vn are linearly independent. So here's an example. These vectors are linearly dependent. And here's a way of writing the 0 vector as a non-trivial linear combination of the vectors. That shows that they're linearly dependent, and this is a linear dependency in those vectors. Here's another example. These vectors are linearly independent. How do we know? In this case, the structure of the vectors makes it easy to tell. Consider any linear combination of these vectors. Summing it up, we get the vector alpha 1, 2 alpha 2, and 4 alpha 3. So if this linear combination equals the 0 vector, it must be that alpha 1 equals 0, 2 alpha 2 equals 0, therefore alpha 2 equals 0, and 4 alpha 3 equals 0, therefore alpha 3 equals 0. So that shows that in that case, the linear combination is trivial. So we've shown that the only linear combination of these vectors that equals the 0 vector is the trivial linear combination. And therefore, these vectors are linearly independent. How can we tell if vectors v1 through vn are linearly dependent? We're not yet in a position to answer that question, but we can relate it to other questions we've already asked. Recall the definition. Vectors v1 through vn are linearly dependent if the 0 vector can be written as a non-trivial linear combination of v1 through vn. Now, by the linear combination's definition of matrix vector multiplication, this linear combination can be written as a matrix vector product, where the columns of the matrix are the vectors v1 through vn, and the vector consists of the coefficients in the linear combination. It follows that vectors v1 through vn are linearly dependent if and only if there is a non-zero vector such that multiplying that vector by this matrix yields the 0 vector. Therefore, the vectors v1 through vn are linearly dependent if and only if the null space of this matrix is non-trivial. This shows that the question, how can we tell if v1 through vn are linearly dependent, is the same as the question, how can we tell if the null space of a matrix is trivial? So we see that once we know how to answer one of these questions, we know how to answer the other one. Here's another example. Consider a homogeneous linear system, that is, a linear system in which all the right-hand side values are 0. Now take these vectors a1 through am and make them the rows of a matrix. Then the set of solutions to this homogeneous linear system is the same as the null space of this matrix. That tells us that this question, how can we tell if the null space of a matrix is trivial, is the same as the question, how can we tell if the solution set of a homogeneous linear system is trivial? So we see that these three questions are really different forms of the same underlying question. Here's yet one more example. Recall that if U1 is a solution to a linear system, then the set of all solutions to this linear system is exactly the set consisting of all vectors u1 plus v, where v belongs to the set of solutions to the corresponding homogeneous linear system. Thus, the questions we've asked are also the same as the question, how can we tell if a solution u1 to a linear system is the only solution to that linear system? So we've seen that all these questions are really disguised versions of the same question. Answering these questions requires an algorithm. So this is a fundamental computational problem, testing linear dependence. Given a list of vectors v1 through vn, determine whether they are dependent or independent. And we'll see two algorithms for this later on. Now, in minimum spanning forest, a zero vector can be obtained by taking the vectors that correspond to edges that form a cycle. So in such a sum, for each node or each label, there are exactly two vectors that have a 1 in that position. So cancellation gives you a 0. So for example, take the vectors corresponding to main Riston, main Keeney, and Keeney Riston. In each position, there are an even number of 1s. So by summing these vectors, we get the 0 vector. Now, if you have a set of edges that include a cycle as a subset, then there is a linear combination of the corresponding vectors that equals 0. So take the vectors corresponding to the dark edges in this diagram. They are linearly dependent because a subset of those edges forms a cycle. So we can write the 0 vector as a linear combination of the vectors corresponding to these dark edges. We assign coefficients 1 to each of the first 3 and 0 to the last. And summing them up, we get 0 for each position. So we see if a subset of S forms a cycle, then S is linearly dependent. On the other hand, if a set of edges contains no cycle, that is, if it's a forest, then the set of edges corresponds to a linearly independent set of vectors. In this case, the dark edges form a forest. There are no cycles. So the corresponding set of vectors is linearly independent. In general, a subset of a linearly independent set is a linearly independent set. In the case of graphs, if the set of edges forms no cycle, then taking away edges from that set, you still can't form a cycle. So let's go through the proof of this lemma. Let S and T be two subsets of vectors, and suppose S is a subset of T. We want to prove that if T is linearly independent, then S is linearly independent. Now, that's equivalent to the contrapositive. If S is linearly dependent, then T is linearly dependent. And we'll prove it in that form. The idea is very simple. If you can write 0 as a linear combination of some vectors, then if you throw in some more vectors, you can certainly write 0 as a non-trivial linear combination of all the vectors. You can just assign 0 to the extra vectors. So let's go through that formally. So we'll write T as this set of vectors, where S is the subset consisting of the first n. Now, suppose that S is linearly dependent. That is, there are coefficients, not all 0, with which you can write a linear combination that equals the 0 vector. Well, we throw in the additional vectors, t1 through tk. The same linear combination, together with 0 coefficients on the additional vectors, still gives us the 0 vector, and it's still a non-trivial linear combination because at least one of the alpha 1 through alpha n is non-zero. Well, that shows that the set of vectors in big T is linearly dependent, and that proves the lemma. Here's another lemma that's going to be useful in reasoning about linear dependence. Let v1 through vn be vectors. One of these vectors, vi, is in the span of the other vectors if and only if the 0 vector can be written as a linear combination of all these vectors where the coefficient of vi is non-zero. In graphs, for example, the linear dependence lemma corresponds to the fact that an edge is in the span of some other edges if and only if there's a cycle consisting of some of those other edges together with the edge. Let's go through the proof. The proof has two directions, like many if and only if statements. Let's do the first direction. Suppose vi is in the span of the other vectors. That is, you can write vi as a linear combination of all the other vectors. Now, we just move vi to the other side, and we get this equation. Well, here, we've written the 0 vector as a linear combination of all the vectors, including vi, and vi's coefficient is not 0. That proves one direction. Let's prove the other direction. Suppose there are coefficients such that the 0 vector can be written as a linear combination of all the vectors where the coefficient of vi is non-zero. Divide all this by that coefficient, and you get this equation. And now we can move everything to the other side except vi, and we've managed to express vi as a linear combination of the other vectors. That proves the other direction. We can restate this in the contrapositive. This is an equivalent statement. Vi is not in the span of the other vectors if and only if, for every linear combination equaling 0, the coefficient of vi must be 0. We'll use this to argue about the Grow algorithm. We'll show that the vectors obtained by the Grow algorithm are linearly independent. In graphs, that means that when you run the Grow algorithm, you'll end up with a forest, a set of edges that contain no cycle. So now let's prove this corollary. For n equals 1, 2, and so on, let Vn be the vector added in the nth iteration of the Grow algorithm. And we'll show by induction that the vectors v1 through vn are all linearly independent. Here's the basis of the induction. For n equals 0, there are no vectors, so the claim that they are linearly independent is trivially true. Assume the claim holds for n equals k minus 1. The induction step consists of then showing that it's true for n equals k. The vector vk added to S in the kth iteration is not in the span of the previously added vectors v1 through vk minus 1. Therefore, by the linear dependence lemma, if you write 0 as a linear combination of the vectors v1 through vk, it must be that the coefficient of vk equals 0. You can rewrite the equation this way without vk, but by the inductive hypothesis, the claim for n equals k minus 1, the vectors v1 through vk minus 1 are linearly independent. So that implies that all these coefficients must be 0. And that shows that the linear combination is trivial. And that is that the vectors v1 through vk are linearly independent. And that proves the claim for n equals k. By induction, it proves the whole corollary. Let's look at the shrink algorithm. When the shrink algorithm stops, the set of vectors in S is linearly independent. In graphs, that means the shrink algorithm produces a forest. We're going to use the superfluous vector lemma. Remember that for any set S of vectors and any vector v in S, if v can be written as a linear combination of the other vectors, then v is superfluous. The span of S without v is the same as the span of S with v. And now we prove that the shrink algorithm eventually produces a linearly independent set of vectors. Let v1 through vn be the set of vectors obtained by the shrink algorithm, and assume for a contradiction that these vectors are linearly dependent. That means that the 0 vector can be written as a non-trivial linear combination of these vectors. That is, a linear combination in which at least one of those coefficients is non-zero. So let alpha I be one of those non-zero coefficients. By the linear dependency lemma, then, vi, the corresponding vector, can be written as a linear combination of the other vectors. By the superfluous vector lemma, we don't need vi. The span of the set without vi is the same as the span with vi. But that means that the shrink algorithm would have removed vi because it wasn't necessary. That completes the proof.